Welcome back to FutureVerse and to episode 2 of our quantum computing series. In the last episode, we explored what a quantum computer is and how it differs from the classical computers we use every day. Today, we're diving into one of the most fascinating parts of quantum computing, the qubit. What is a qubit? How does it work? And why is it so powerful? Let's begin by looking at the basics. In classical computers, like your phone or laptop, information is processed using bits. A bit is binary, meaning it can be either a 0 or a 1. Every website, image, or app you use is built using combinations of these simple binary digits. But qubits, short for quantum bits, are different. Thanks to quantum mechanics, a qubit can exist in a superposition of states. That means it can be 0, 1, or both at the same time. To understand this, imagine flipping a coin. While it's spinning in the air, it's not just heads or tails, it's kind of both. That's similar to how a qubit behaves, and it's this property of superposition that gives quantum computers the ability to process an enormous number of possibilities at once. Now let's add another strange and powerful concept, entanglement. When two qubits become entangled, they're no longer independent. If you measure one, the state of the other is instantly known, even if they are light years apart. This isn't science fiction. It's been proven again and again in labs around the world. Einstein famously called it spooky action at a distance. Entanglement allows quantum systems to be deeply connected. It lets qubits work together in complex ways that are impossible with ordinary bits. In practical terms, it means quantum computers can solve certain problems exponentially faster than classical computers ever could. But creating and controlling qubits isn't easy. They are incredibly delicate and must be kept in special environments to function. Some of the most common ways to make qubits include superconducting circuits, which use tiny loops of wire cooled to almost absolute zero trapped ions, where atoms are held in place with electromagnetic fields, photonic qubits, which use particles of light, and even diamond defects, where tiny flaws in diamonds are used to trap electrons. Each of these methods has its pros and cons, and scientists around the world are still experimenting to find the most stable, scalable approach. One of the biggest challenges is decoherence, when a qubit loses its quantum state due to interference from its surroundings. Even small vibrations or temperature changes can disrupt a qubit, so quantum computers require ultra-cold environments and isolated chambers to operate reliably. So why go through all this trouble? Because the potential is massive. With qubits, quantum computers can simulate the behavior of molecules, which could lead to breakthroughs in medicine and chemistry. They can optimize supply chains, improve weather forecasting, and even make machine learning models faster and smarter. And in cybersecurity, they might someday crack codes that are impossible to break with today's computers. Qubits are the foundation of this revolution. They are not just quantum versions of classical bits. They represent a completely new way of processing information. Understanding qubits is key to understanding the future of computing. Thanks for watching episode 2. In the next episode, we'll explore how scientists are building actual quantum computers and what it takes to scale them up for real-world use. If you're excited about the future, hit that subscribe button and join us here at FutureVerse as we continue to decode tomorrow's tech.